Hello and welcome. This is our work, Deep Factorized Metric Learning. In this work, we factorize the training signal and employ different samples to train various components of the backbone network. And we further devise a learnable router to adaptively allocate the training samples to each subblock with the objective to capture the most significant information. Our method can boost the performance of existing methods of deep metric learning in both image clustering and retrieval tasks. There are three problems in machine learning. The first one is the classification problem, which learns the characteristics that distinguish a sample. And the second one is the regression problem. It learns to fit a certain value that describes a sample. And the last one is the metric learning problem, which learns the relations between samples. As we all know, deep metric learning aims to group similar images together and separate them from dissimilar ones. Two conventional paradigms include the contrastive and the triplet paradigm, which are based on sampled pairs and triplets, respectively. Conventional deep metric learning ignores intraclass variance and might lead to overfitting to insignificant characteristics, which causes bad generalization on unseen classes. Therefore, several ensemble-based methods are proposed. For example, some of them divide embedding vectors to learn diverse characteristics to improve the generalization ability of this method. However, the backbone network still receives mixed training signals from samples. Additionally, the final performances are always limited by the dimensions of the embedding vectors. Under such circumstances, we propose to factorize the backbone modules to obtain diverse characteristics, and we adaptively update different modules with different samples. Specifically, we employ discriminative deep metric learning laws on factorized embeddings. We devise learnable routers for the training samples, and we force the factorized embeddings to encode the most significant information. During implementation, we choose the vision transformers as our backbone because they are more modularized. We factorize the multi-head self-attention and multi-layer perception blocks in vision transformers to receive signals from diverse training samples. Our deep factorized metric learning framework is compatible with various loss functions and architectures. We conduct the experiments on three widely adopted deep metric learning datasets, and they are all divided into training sets and test sets. These are our ablation studies. We adopted different numbers of subblocks to test the performances of deep factorized metric learning. In addition, using different loss functions also influenced the results to a certain extent. We also verified the effects of the backbone architectures. In this table, DEITX models are pre-trained on the ImageNet 1K dataset, and the VITX models are pre-trained without the distillation token, but might be on the larger ImageNet 21K dataset. We observed that deep factorized metric learning consistently outperforms the baseline architectures. We compared our method with state-of-the-art methods. We see that deep factorized metric learning improves the performances of existing losses and sampling strategies. We tested the effectiveness of the factorized network on the ImageNet 1K dataset. We see that deep factorized metric learning can effectively maintain the performances of the original network with significantly less computation. The visualization results of diversity of the factorized network show that different subblocks learn to process diverse training samples, and deep factorized metric learning extracts diverse characteristics from the input images. To sum up, we factorize the training signal and employ different samples to train various components of the backbone network. And we further devise a learnable router to adaptively allocate the training samples to each subblock with the objective to capture the most significant information. Our method can boost the performances of existing methods of deep metric learning in both image clustering and retrieval tasks. Thank you.